assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
In this problem, we're given the decay rate of potassium-40 isotope, and we're asked to determine how much of it is present in a 1 liter glass of milk. The only information that we're given is the decay rate of potassium-40, given 42 decays per second. We can go to Appendix B and look up the decay constant for potassium-40. You'll find that the decay constant is 1.248 times 10 to the 9th years. We know that decay rate is equal to the product of the decay constant times the amount of substance in terms of number of nuclei n. Dividing both sides by the decay constant, we realize that we can find the number of potassium-40 nuclei from the decay rate given the decay constant that we just looked up from Appendix B. Plugging these in, we have 42 decays per second for our decay rate, but we have to convert our decay constant from years into seconds. So it will, to correspond with the decays per second decay rate that we're given. So we enter in the decay constant in years, multiply it by 365 days per year, and multiply that by 86,400 seconds in a day. That gives us a numerator that seconds cancel, and we're left with simply decays. And you'll recall that the expression for the decay rate involves a natural log of 2, which has the decimal approximate of 0.69. Since our decay rate is reciprocated in this relationship, this natural log of 2 ends up on the bottom. When you plug in all of these numbers, you'll find that the number of potassium-40 isotope atoms in this 1 liter glass of milk is 2.385 times 10 to the 18th. We are asked, though, to find the amount of potassium-40 in terms of mass. So doing that, we can find the atomic mass of potassium-40 and use the milligram, well, actually it's kilogram, but if we add 6 to the exponent here, we can have a molar or an atomic mass of conversion factor in terms of milligrams. Recall that this atomic mass is in terms of atomic units, so these atomic units U will cancel in this expression. And we find multiplying our 2.385 times 10 to the 18th times the molar mass of potassium-40, I'm sorry, not the molar mass, the atomic mass of potassium-40 times our conversion constant gives us 0.16 milligrams of potassium-40 in 1 liter of milk. The second part of the equation asks us to find how much potassium-39 is in the milk as well, given that we know how much potassium-40 is in the milk. This problem can be solved by finding the relative abundances of each isotope of potassium in Appendix B. And with those relative abundances, we can set up a proportion to determine the proportional amount of potassium-39 given this 0.16 milligrams of potassium-40 is in the milk as well. Setting these up, there's a 93% abundance of potassium-39 naturally, and there is a 0.0117% abundance of potassium-40, which in our specific case, we have 0.158 milligrams of it. So simply multiplying both sides by our 0.158 milligrams gives us 1.260 milligrams, or 1.26 grams of potassium-39 in our 1 liter of milk.